Hi everyone, so it is time again to do our next lesson. We're doing section 6.3, which is higher degree polynomials. So today we're going to be talking about a concept called end behavior, and we're going to kind of start to learn how does the polynomial function relate to its graph. So before we get started into the lesson, we're just going to do a quick review. So based on a polynomial function, which is one we have here, remember that this form, let me get to my stylus, is called factored form. All right, so the zeros of f of x, remember we changed the sign. So if our factor is x minus 3, then our 0 is 3. Because remember, if we set x minus 3 equal to 0, and that's what we're finding is what x values cause y to equal 0, you solve for x and you get x equals 3. So essentially it's like changing the sign. Really what you're doing is setting your y equal to 0 and solving the equation. So you set each factor equal to 0 to get your zeros. So what are our zeros? Our zeros are 3, 5, and 4. What is the degree of f of x? Well, normally when we find the degree, if we're in factored form, we count the x's. So if we count, we have 1, 2, 3, except this x actually has a multiplicity of 2, so it appears twice. So because of that, we actually have 1, 2, 3, 4, and we end up with a degree of 4. This is a fourth degree polynomial. What are the roots? Well, we don't have any imaginary factors or complex factors here, so the roots would be the same as the zeros, which would be 3, 5, and 4. How many roots should f of x have? Well, technically, since it's a fourth degree polynomial, it should have 4 roots because the degree is 4. Because degree is 4. We instead have 3 roots, but one with a, remember this big word, multiplicity of 2. So technically, this 4 is what we would call a repeated root, or a root with a higher multiplicity. Okay, so quick review. We are going to actually find the volume of a box. Now, this figure right here doesn't really look like a box, but it is a box. What I want you to think of is if you fold these sides, if you take this side right here and fold it along this line, fold it up, and then do the same on all the dotted lines, what you get is an open box. It doesn't have a top, but it is the box itself, and we're finding the volume of this box. So to find the volume, I'm going to erase those extra lines. To find the volume, we are going to multiply length times width times height. Well, the length would be 30 minus 2x, and the width would be 30 minus 2x. The height would be the height of these flaps that we're folding up. So the height of the box is x. If we multiply these things together, here's what we get. So we're going to distribute. We get 900 minus 60x minus 60x plus 4x squared. And then this would be times our x that's sitting out there. Combining some like terms, we get 900 minus 120x plus 4x squared times x. So if we distribute this x in, we get 900x minus 120, that's a 120x squared plus 4x cubed. Now, this is technically correct, but when we write a polynomial, it's always best to write it in descending order. It's helpful for a whole bunch of reasons. So we're going to put the cubed term first, then the squared term, and then the linear term here, this 900x. All right. And this is the same as what we've got graphed up here. Now, a little discussion about graphs. So we know, if we were to graph this function, we've got a couple of zeros. We have a zero here, and then we have a repeated zero right here. So we've got two zeros, and that makes sense. Really, technically three roots, but one is repeated. There's the zero, and then there's the one that's repeated, right? So we have our two roots. But we also have something that we're kind of learning today, which is we have a maximum value. So that's the highest value on the function. And we have a minimum value, which is the lowest value on the function. Now, you can't tell the max and min just by looking at an equation. There's no way to look at an equation and figure out the maximum and the minimum unless the equation is really simple. But if you're talking about a cubic, it takes a little bit of work to find that the max and the min. But by looking at a graph, it's easy to see. So the maximum is the highest point, not the highest point on the entire graph, because obviously this graph keeps going up to infinity and down to negative infinity. However, it's kind of king of the hill here. So it's the highest point relative to the points on either side. So this point that's king of the hill, that's why this is called a local maximum, not the absolute maximum. And then same thing for this minimum. It's kind of the bottom of the valley here. So it's lower than the points on either side. And it's the lowest point if you kind of like localize the area. So if I said, hey, what's the minimum in this little area? You would say, oh, it's right there. That's the local min. So we have a local max. We have a local min. Local max is king of the hill. Local min is bottom of the valley right here. All right, long run or end behavior. So your book calls this long run behavior. I have to just tell you right up front, I am always going to call it end behavior. So just get used to me calling it end behavior because that is how I've always called it. Okay, so here's the thing. When you have a polynomial and you've got this leading term, this a sub n x to the n, and then you have all these other terms after it, all the other terms are really important when you're kind of looking at the middle of the graph. They make the graph look really different. But when you zoom out and you're just looking at what happens at the far ends, and we talked about this before, the far ends are way out when x gets closer to infinity and when x gets closer to negative infinity. Way out at the ends, this giant polynomial really starts to just look like the same as if it was just the leading term. And I'm going to show you that a little bit in Desmos, and you'll be happy to know that I pre-graphed the functions in Desmos. So we have the red function is y equals 4x cubed, and the blue function is y equals 4x cubed minus 120x squared plus 900x. And looking at these two graphs, they look really different. They're both cubic, but the graphs themselves look really different. However, if we start to zoom out, now they still look different, still look different, still look different, but notice that this middle part right here is becoming more and more insignificant the more we zoom out. And so as we zoom out further and further, the graphs kind of start to fall right on top of each other. And that middle part doesn't really matter so much. What we're talking about now is just these ends. So what's going on down here and what's going on up here. Now, it's hard to think that down here is where x approaches negative infinity and up here is where x approaches infinity. But you have to remember this is a really steep growing graph, and it does keep going all the way to infinity in both directions. So the main thing to remember is that as you zoom out, doesn't matter all the other stuff that's in the equation. What really matters is the leading terms. Those leading terms kind of drive the graph. So this 4x cubed and this whole big equation end up looking very similar when you zoom out and you just start looking at the ends. Okay, and this is just a recap so that it's in the slides, so that if you're looking at just the slides, same thing. If you zoom out, eventually they're just going to lay right on top of each other. All right. Find a polynomial function whose graph has x. I think I'm going to back up and say one more thing about end behavior. So we talked a little bit in the past. I can't move this over, but I'm going to write down here. So when we were talking about end behavior a couple days ago, we said as x, oops, hang on. Let me rewrite this. I'm going to move it over. As x approaches infinity, what does y approach? And as x approaches negative infinity, what does y approach? So for this graph, as x goes out to infinity, what is our y value pointing at? Our y value is pointing up to positive infinity. And as x goes to negative infinity, we're looking to the left. What is the left end doing? It's pointing to negative infinity. So our right end behavior, the right side of our graph, if it's pointing up to infinity, then it's infinity. Our left end behavior, what's going on the left side of our graph, is pointing down to negative infinity. And so this is another way to write our end behavior. Okay, let's move on. Find a polynomial function whose graph has these x-intercepts and a y-intercept at 180, then describe the features of its graph. So when we're only given these three x-intercepts, we honestly don't know for sure what kind of a polynomial it is. For all I know, this 3 could be a repeated 0. It could have be repeated 5 times for all I know, and the 5 could be repeated twice. There could be complex roots that they didn't mention, and all kinds of stuff going on. But for our simplest polynomial, which is what I think we should do, we're just going to write it in factored form, just assuming that these are just 3 simple roots. So what we have here is y equals a times x minus 3 times x minus 5 times x plus 4. And then if we wanted to solve for it, first let's go ahead and multiply this together, just for the heck of it. But no, you know what? Let's just leave it in factored form. We have a y-intercept of 180. That means that when x equals 0, our y is 180. So we negative 3 times negative 5 times positive 4, setting all of our x's equal to 0. So we get 180 equals, so 60a, divide by 60, and you get a equals 3. So our final equation in factored form would be 3 times x minus 3 times x minus 5 times x plus 4. All right, so let's sketch this graph. So, okay, so we have a 0 at 3. We have a 0 at 5. We have a 0 at negative 4. And then we have some y-intercept way up high at 180. 180. Whoops. Let's not turn out those. So that's 3, that's 5, that's negative 4. Okay, so in order to sketch this graph, if our leading coefficient is positive, like it is, that means that we're going to follow the same end behavior that we had on the previous screen. Whoops, yeah, the previous screen. So if our leading coefficient is positive, that means that to the left, we're going to point down, and to the right, we're going to point up. This works anytime your degree is odd. So if a first degree, third degree, fifth degree, any odd degree, when you have a positive leading coefficient, the left side's going to point down and the right side's going to point up. So we know our left side is going to point down and our right side is going to point up. What we don't know is what's happening in between, right? So if we just kind of had to roughly guess, we don't want any kind of weird jumps or sharp points or anything. So to just kind of create a smooth curve, I'm just going to pass my graph through the points that I know. Pretend that connects. And there's my rough sketch of the graph. Now, I don't know if this is correct. I actually do know that it's not exactly correct, but that's okay. It's just a rough sketch. It follows all the directions. It has the 3 zeros. It has the correct y-intercept. And the end behavior, the ends are pointing in the right way. So when we have a positive leading coefficient, that means that our left end is going to point to negative infinity and our right end is going to point to positive infinity. Left end points down, right end points up. Here's the actual graph. So the actual graph, here's that y-intercept of 180. Here's your x-intercepts -4, 3, and 5. Notice our end behavior, we got that right. But what we couldn't tell from the equation was the local max and the local min. So our local min looked actually pretty good. It looks like it fell right around 4. But the local max here, I just didn't get it up high enough. So our local maximum is actually right here. There's no way to know that from the equation without doing a lot of work on the side, which we're not going to get into now. All right, so if we have to identify the degree of a polynomial, so remember, if the ends are pointing in opposite directions, so if the ends are opposite, meaning one's pointing down and one's pointing up, opposite, that means that the degree is odd. So odd degree means, think O for odd, O for opposite. Odd degree means that those ends are going to point in opposite directions. How do we know which way they're going to point? If our leading coefficient is positive, the left end will point down and the right end will point up. If the leading coefficient is negative, the left end will point up and the right end will point down. Why? What does that negative do? Let's bring back some old concepts. The negative reflects the graph over the x-axis. So since this negative flips it upside down, it flips our end behavior. And so it changes the way that the graph is pointing. So if our leading coefficient, there we go, is positive, that means as x approaches infinity, y approaches infinity. As x approaches negative infinity, y approaches negative infinity. And if our leading coefficient is negative, it's going to do the exact opposite. As x approaches infinity, y approaches negative infinity. As x approaches negative infinity, y approaches infinity. And the graph doesn't have to be a simple cubic. This cubic here, which has some local maxes and mins in the middle, still follows end behavior. We're just looking at the ends. So if your leading coefficient is positive, left points down, right points up. Leading coefficient is negative, left points up, right points down. All right, so if we had to sketch a fifth degree polynomial with a positive a, so a fifth degree means it's going to have, well, we can guess that it could have 5 different x-intercepts. It doesn't have to. It can have 3 and have some be repeated. But we're just going to sketch a fifth degree. Let's just throw 5 x-intercepts on here. So I'm just going to roughly evenly space them. 1, 2, 3, 4, 5. There's our 5 x-intercepts to go with our fifth degree. All right. A positive a means that our right end is going to point up and our left end is going to point down. And then how do we fill in the middle? You kind of follow the trend. So you kind of give it a local min here, and then a max, and then a min, then a max, and then we end up with our polynomial. So a fifth degree polynomial, still odd, right? So it's still going to follow the same logic. Positive a means left points down, right points up. Fifth degree means at most 5 x-intercepts. So it's easiest to just go ahead and plot all 5. The other thing to keep in mind is that the number of hills and valleys is at most 1 less than the degree. So for a fifth degree, we can have at most 4 hills and valleys. So meaning local max, local min, local max, Vogelman. All right, last two examples, and then we're done for the day. Write a polynomial function with real coefficients and these zeros. So traditionally, we would write this zero, we'd write the factor x minus 2, and for this zero, we'd write the factor x plus 5. But now we've got this lovely, beautiful complex zero, which we're going to write as x minus 3 plus 4i. But when we have a complex zero, we must also include its conjugate. What is the conjugate of 3 plus 4i? 3 minus 4i. So whenever you have a complex zero, like this one, you must include the conjugate, this guy. And how do you find the conjugate? You just change the sign that separates those two terms. Notice it's still x minus. The only thing that changes is the sign inside of the complex number. So if we go from 3 plus 4i to 3 minus 4i. When I multiply these kinds of polynomials out, if you have to expand it, which you will have to do, I like to do the real, go ahead and multiply the two real factors first. So we have x squared plus 5x minus 2x minus 10. And then I like to do the complex separately. So think of it, I'm going to rewrite these. I'm going to distribute the negative. X minus 3 minus 4i times x minus 3 plus 4i. And you multiply them out just like you would distribute any other polynomial. This one I'm going to go ahead and combine. So we have plus 3x minus 10. Okay, so I'm going to do x times all of these terms. So x squared minus 3x plus 4ix. Oh, that 4 didn't turn out well. There we go. All right, next I'm going to do negative 3 times all three of these terms. Minus 3x plus 9 minus 12i. And then the last thing I'm going to do is negative 4i times all these terms. I'm going to write down here negative 4ix plus 12i minus 16i squared. Now, if you do this right, all of your I terms should cancel out. Plus 4ix minus 4ix, plus 12i minus 12i. So when we rewrite it, we get x squared plus 3x minus 10 times, and then we get x squared minus 3x, I'll combine in a minute, minus 3x plus 9. What do we do with this negative 16i squared? What does I squared equal? And remember, that's right, it's negative 1. Okay, so let's clean it up. X squared plus 3x, oh, it's getting bad, minus 10 times x squared minus 6x. Okay, and then this becomes 9 plus 16, which is 25. All right, we are so close. Now we've got to distribute these three terms times these three terms. I'm going to start with the x squared. So I have x to the 4th minus 6x cubed plus 25x squared. Now my 3x, I have plus 3x cubed minus 18x squared plus 75x. And then my negative 10 minus 10x squared plus 60x, and then minus 250. So my final answer, which is, you can't tell, it's really faint down there at the bottom, so is y equals x to the 4th. I'm going to underline as I go. So there's done. Okay, let's find the cubes. Minus 6x cubed plus 3x cubed. So I end up with minus 3x cubed. Now let's do the squareds. So I'll put these in green. Plus 25x squared minus 18x squared minus 10x squared. So it's like 25 minus 28. So we end up with minus 3x squared. Okay, now we go to our x's. We have 75 plus 60. So we end up with, okay, plus 135x. And then finally, the constant term minus 250. And there's our polynomial. Woo! And there it is. Woo! Okay. Notice this graph. We have those two zeros that were given to us, the -5 and the 2. You won't see an x-intercept for the imaginary zero because it's imaginary, and this is a real number coordinate system, so you'll only see x-intercepts for the real zeros, not the complex zeros. And then there's your y-intercept right there. All right, last example, and which is just another practice at doing the same thing, just to make sure you've got it. What I'd like you to do is take a second and pause, see if you can work this out on your own before I work this out for you. So try this on your own, see what happens. All right, so I'm going to set this up. So I have y equals x plus 3 times x, because x equals 0, times x minus 1 plus I times x minus the conjugate 1 minus I. All right, so that first it says name the missing zero. That is the missing zero. That 1 minus I is the missing zero. All right, so our y equals, so multiplying these two together, I get x squared plus 3x. And now I'm going to just clean up my complex conjugates. So I have x minus 1 minus I times x minus 1 plus I. And I'm just going to work with the complex portion. It's easier to do those together first. So multiply x. So I have x squared minus x plus ix. Then the -1 times all three terms minus x plus 1 minus I. And then the -I times all three terms minus ix plus I minus I squared. All right, if we combine our like terms, we get x squared. Whoops, I keep hitting the wrong thing here. So minus x. So, oh, and notice this plus ix and minus ix, those are gone. Minus I plus I, those are gone. So we end up with minus 2x, and then we have a plus 1, and we have a minus I squared. So what is minus I squared? This is minus -1, which is like another plus 1. So it's kind of like we have plus 1 plus 1. So we have plus 2. All right, now we can start distributing this guy. So we're going to do x squared times each of these. So I get x to the 4th minus 2x cubed plus 2x squared, and then 3x times each of these. So I get plus 3x cubed minus 6x squared plus 6x. And putting everything together, x to the 4th plus x cubed, and it's sometimes helpful just kind of underline as you go, plus 2x squared minus 6x squared is minus 4x squared, and then plus 6x. And there's our